Okay, we've been talking about biorthogonality and in Rn. And now we're going to extend this to Hilbert spaces. Rn is a Hilbert space with the standard inner product. But not all Hilbert spaces are in Rn. So once again, we're going to assume that we can that we have some basis that spans a finite dimensional basis set. And here I put it as a function of t. It doesn't have to be, but it could be. Okay, now we'll choose x to be an arbitrary signal in that space, and we know that the closest point in S to x is, well, x itself, so we can just write x of t is equal to the sum alpha n psi n of t, like this. And we already know, we've seen this, we've done it before, how to get our alphas. So put this back into vector form, and we know that we have to take the inverse of our Gramian matrix, and writing this out is a little bit tedious, so we'll just we've run across this before, psi n psi 1 down to psi n psi n. We take the inverse of that matrix, then we multiply it by our projection of x onto the same basis. I keep saying that. Let me just say the inner product of x with the respective basis functions. Okay, so let's let H be the inverse of our Gramian matrix, the Gram matrix. Then we can write alpha n is just equal to the sum. It's going to be like so. Alpha 1 will be the top row multiplied by the column matrix over onto our right, and so since we've already defined this as a matrix H, I'll use that notation. So H, going over the nth row, and L is indexing each column in that row, and then we multiply that by x with dot product with psi L. So the inner product, those form the column elements there of our matrix, or B matrix, or B vector on the right. So just another way of writing it. But we can move that sum inside our inner product, get x, and now we have inner product with the sum of h n comma l times psi l. Okay, so now we can write the x of t, which is equal to the sum n equals 1 to n. We're going to put x with psi tilde of n times psi n t, if it's a function of time, but it's just to indicate we've got that vector, where psi tilde n of t is equal to the sum l equals 1 to capital N of h n comma l psi l of t. All right, so let's look at an example of what this does. We'll let S be the set, the space rather, of all second order polynomials on 0, 1. And so it should be obvious that we can define a nice simple basis like this. So you can build up any polynomial by linear, second order polynomial by linear combinations of those. So now what? Define H inverse to be, we define H to be 1, 1/2, 1/3, 1/2, 1/3, 1/4, 1/5, 1/4, 1/3 inverse, where this is, in other words, it's the inverse of the Gramian. The standard inner product of y1 with y1 is 1, y1 with y2 is 1/2, and so on and so forth. And so this gives us an interesting matrix, much bigger than what we had before. Like so. And so then we can just read off our tilde functions in this case. It's going to be 30t squared minus 36t plus 9 is our first one. So that's right here, where the first column corresponds to 1, next corresponds to t, next corresponds to t squared. And so psi 2 tilde t is equal to minus 180 t squared plus 192 t minus 36, and similarly for psi3, we get 180t squared minus 180t plus 30. Okay. So basically this looks just like it did before when we looked for biorthogonal bases in Rn, except that since we're not dealing with specifically values in Rn, we had to generate our transformation from the Gramian matrix instead of just directly from the inverse of the function in Rn. Okay, so the vectors in Rn. All right, so one last point, and that is that we can have biorthogonal bases in infinite dimensions. Now, inverting infinite matrices suddenly gets really tricky. So we have to think about it yet a different way. And I'm just going to summarize some of the concepts here and give you a few examples. And then we're going to go in and discuss splines, which are a very useful application and example of non-orthogonal bases in the next lecture. So if we have an infinite dimensional subspace, then a set of vectors is linearly independent if no finite subspace is linearly dependent. Because remember, we have this concept, we can approximate vectors with infinite sequences. And so it kind of flies in the face of how you define linear independence. But this provides a way of thinking about the problem. Okay, so the reason for this, once again, is that if we have, it's possible that you could have an infinite sequence of vectors within this infinite dimensional subspace, which could approximate any other vector in that space. And so linear independence has to be thought of this way instead. But now let's go ahead and define a new concept. That of a Riesz basis. Okay. So we say that the set of vectors psi sub n, which is potentially infinite here, is a Riesz basis if there exists, actually if there exists constants that are greater than 0 and less than infinity, such that A times the sum of the transform coefficients is less than or equal to the norm squared of our reconstruction less than or equal to b times the sum of the absolute transform coefficients, like that. So, and this has to be true for all sequences of alpha n that are finite. If everything's infinite, it doesn't really make much sense to talk about it. So, in this case, if we have an orthonormal basis, then A is equal to B is equal to 1. So what is this saying? Well, if A equals B is equal to 1, then we have Parseval's theorem, which basically says that the sum of the norm of the sequence squared is equal to the sum of the absolute values of the transform coefficients squared. And so that's beautiful. If we don't have that, then it's possible that somehow in taking our transform we're distorting it in some way. But we may be able to get back with the biorthogonal transform, as we've discussed. But it's stating that the transform coefficients don't reflect directly the energy of the sequence, but there are some bounds, and these bounds are really useful because if we have a small change in the coefficients, we'd like to see a small change in the signal, or a small change in the signal should be reflected by a small change in the coefficients. That's what Parseval guarantees us. Here we don't have that, but we do have some bounds. Maybe a small change in the coefficients leads to a slightly larger change in the signal itself, but at least there are some bounds and some scaling that we can understand and get our hands around with respect to that. So let's look at just a few examples and see how this plays out. So an example that is not a Riesz basis is a set. Once again, we're looking at the continuous signals on 0, 1. And we define these signals. So this is going to look something like this. Just a ramp up and a ramp down. Then we can define psi 0 of t to be a hat function. So that would look like square root of 3t, 0 less than t less than equal to 1/2, and square root of 3, 1 minus t for 1/2 t up to 1. And let's scale that then to define the full basis of some kind on this infinite dimensional set. j greater than or equal to 1, and n equal to 0 up to 2j minus 1. Okay, so this function is going to look like that. And then the scaled versions are going to be something like this. So here we have our psi of 1 comma n, t being these colored ones. And 2 comma n, we're just going to be packing more and more triangles in next to each other, these little hat functions. So it turns out that this is going to be the set of all piecewise linear functions. So instead of piecewise constant like we had with the Haar wavelet, this is piecewise linear. And since this is dense, we can make smaller and smaller linear approximations. We can get closer and closer to arbitrarily close to any signal in L2. So this is great. We can define anything we want. However, this sequence might not be well behaved. So what could cause it to blow up? Well, with this particular sequence, let's say we had a function like that, 0 to 1. Well, you could see that this could easily be approximated by something like this. And there we go. And so we have this nice approximation. But it could also be approximated by linearly interpolating between all of these terms with a set of small triangles instead, and so on and so forth. So we could approximate this in 2 ways. Well, what's the impact of that? The impact of that is that we could, say, have a first approximation that exactly equaled it, and a second approximation that exactly canceled it, and a third approximation with different sized triangles that also exactly equaled it. We could scale the first 2 arbitrarily, which would mean the sum of our alpha coefficients could be infinitely large, or they could be quite small. So in this case, there are many ways to approximate this function. And so the alphas may have absolute sum. Okay. So that's one example. Another example is non-harmonic sinusoids. So it turns out that with non-harmonic sinusoids, under a few conditions, they form a nice Riesz spaces. And these are discussed a little bit further in the printed class notes that you can take a look at. So let me just make a note. Form a Riesz spaces. if some conditions are met. And basically, the conditions have to do with the fact that the sinusoids used have to have frequencies that are relatively close to being to the harmonic frequencies, and in some they basically have to be within 25% of an integer multiple of the harmonic harmonic frequencies. And if this is the case, then you can define a Riesz basis, and the A and the B vector values are a function of this maximum deviation from a purely harmonic sequence. So let's put C notes for that one. And let's see. Just a few more points about this. I apologize for the length of this lecture. There's a lot to cover, and I didn't know what would be the best stopping point in between. But if we have, for example, a Riesz basis in a Hilbert space, then it turns out that there is a dual basis. Now, since this Riesz basis is infinite, it's not going to be quite as easily computed as it was in our previous cases, because we can't invert infinite matrices. And so the approach, we're not going to cover the general approach here, but I will say that the general approach involves using basically, oh, I'm sorry, lost my train of thought. Okay, yeah, so the basic approach uses operator theory to arrive at the dual basis functions when you're manipulating infinite sequences of things. It's a little bit trickier, but it's possible, and it can be done. So once you have a Riesz basis, you can do linear approximation just as we could before. But as I've mentioned, we don't have, in general, Parseval's theorem working for us the way it did before. The way it did before, when we approximated something, we had a good sense for what happened with our approximation. But let's take a look at what goes on in the case of a Riesz basis, and that is that we will have a best approximation, and we can get a handle on the error, but the error is bounded essentially by a scaling factor of A and B. Okay, so if we have some infinite dimensional subspace, then of this space above, Hilbert space S with a Riesz basis psi, then there exists a dual basis such that x hat, being a linear combination of psi sub n, is the best approximation to x in T. So the beauty of this is that there aren't any big surprises. It's saying that yes, even with an infinite dimensional subspace, we do have best approximations within that space. So now let's look at the impact of using a Riesz basis instead of an orthonormal basis. Suppose the n is equal to the inner product of x with, so alpha n is equal to the inner product of x with psi tilde of n, and we perturb this in some way. Typically this is done with quantization, as if we're doing loss decompression or something like that. Then when we reconstruct our sequence, and alpha tilde of n times psi of n, obviously alpha, I said tilde, I meant prime. Alpha prime, x of prime is going to not equal x. So let's find x minus x tilde, or x prime. Made the same mistake again. And that's going to be the sum for epsilon n times psi n. It's going to give us our error sequence. And then we can see that this error, we don't know exactly what it's going to be, but we do know that it's going to be bounded above and below this would be the E vector here, or the epsilon vector. By a B on the upper side and A on the lower side times epsilon. So when we use a Riesz basis, we can indeed represent signals using non-orthogonal bases. We can reconstruct the signals using this biorthogonal basis concept, but we have a problem that if we do any type of approximation within that domain, the error in the actual signal domain may be larger or smaller than we would have expected for a orthonormal basis. So next time we will look at a very useful application of these concepts in B-splines.